lecture number 2 by Professor Marcus.
This is a preliminary. We are surrounded by requirements of correctness, be it logical, grammatical, juridical, moral, or political. From school to university, from professional to academic life, we are under the pressure of some norms of behavior, of some rules that should be respected. On the other hand, as human beings, we look for meaning, for what makes sense, and we should train the new generations to need them, to look for them. Rules and norms are vital in social life. They prevent us to fall in anarchy. They express our need for order, expressed by various forms of correctness. Meaning and sense are equally a vital human need. They give substance to our lives. They are the way we are looking for our creative identity, for our need of truth, of beauty, and of transcendence. Is there a balance between these two trends? To what extent do they need each other? To what extent are they cooperative? To what extent do they stimulate each other? But to what extent each of them develops at the expense of the other? To what extent are they in conflict? These are the questions I will try to answer in this lecture. We will try to approach these questions in the particular case of mathematics and computer science. Like in natural languages, in these fields we distinguish between three levels of analysis: syntactic, semantic, and pragmatic. Correctness refers to the syntactic level, governed by binary predicates and explicit rules. Meaning refers to the semantic level. It is a matter of degree and of typology, instead of binary thinking. The field of syntax. In a usual mathematical text, syntactic problems are mainly related to the validity of some types of inferences, to the use of various logical operations, to the linguistic cohesion of the mathematical discourse, and to the consistency in the iterative use of various terms and symbols. To syntax belongs also the accuracy in using previous concepts and results. All these aspects are usually labeled by the term correctness. It includes also the way we are using deductive inferences, because they are governed by explicit rules, so they belong to syntax. The field of semantics. Semantic problems are mainly related to the choice of primitive terms and of axioms, to the choice of concepts and their definitions, to the choice of problems to be investigated, to the choice of tools and methods to be used, to the way we formulate questions, guesses, hypotheses, and conjectures, to the way we build hypothetical explanatory models and metaphors. Professor David Mumford from Brown University stressed the fact that to build explanatory or hypothetical explanatory models has the same importance as to prove theorems in mathematics. Not like Bourbaki claimed that the only distinguished mark of a mathematician is to prove theorems. Meaning is to a large extent located at the interface of mathematics with other fields, physics, computer science, biology, economics. History of science and its cultural environment are a rich source of meaning, as well as the interaction of various domains of mathematics and computer science. Questions of adequacy, of relevance, and of interpretation are at home in semantics. Syntax and contextual behavior may generate meaning, so there is no sharp border between semantics and syntax. Very important, because to a large extent, mathematical meaning is built by syntactic contextual procedures. A typical case of meaning generated by syntactic contextual means is Hans Freudenthal's cosmic language Linkos, aiming to permit communication with possibly intelligent beings from other celestial bodies. Such a language is supposed to be learned in absence of a meta-language. In other words, Linkos is supposed to function as its own meta-language. For instance, the meaning smaller than of the symbol smaller is learned by means of context of this type. A large part of meaning in mathematics is obtained by syntactic contextual means. Zero, the empty set, the identity element in a group, connectors in logic, categorical symbols in formal systems, in automata, in formal generative grammars, in a Turing machine. The move of mathematics from a quantitative to a structural discipline stimulated the syntactic contextual way to build meaning. This trend became very visible in algebra and then in the explosion of order, algebraic and topological structures in the way Bourbaki did it in the treatise. Another stimulus came from the emergence of the information communication computational paradigm, leading to a strong connection with discrete mathematics, logic, combinatorics, and algebra, all based to a large extent on the syntactic contextual way to build meaning. This accent on the syntactic contextual behavior of a symbol as a way to understand its meaning, instead of the traditional genus differentia way used before, contaminated also other disciplines. So, inspired by logic and combinatorial systems, Chomsky proposed generative grammars where all grammatical categories are defined by their behavior in the generative process. Inductive inferences have a mixed status, partially syntactic, partially semantic. It may be impregnated also with pragmatic elements, related to some implicit presuppositions as those pointed out by Carl Hempel and Nelson Goodman, according to which induction is paced with circularity. Abduction is predominantly semantic. Abduction is a concept introduced by the most important American mathematician of the 19th century, Charles Sanders Peirce. According to Jacques Adamar, who is in his turn follows Henri Poincaré, creativity of any kind proceeds by alternating choices and combinations. The former are predominantly a semantic job, see the frequency of the word choice in the examples of semantic phenomena, while the later are dominated by syntactic rules and favor our ludus, Latin word ludus, trend towards game and play. We are stimulated to try any possible combination, irrespective of its meaningful or meaningless nature. All these things happened by contribution of both conscious and unconscious factors, not only in science but in art too. Adamar refers in this respect to some reflections by Mozart. However, there is a danger to extrapolate beyond any limit our syntactic capacities and to reach in this way what Eric Bishop, the creator of constructive analysis, called the schizophrenia of contemporary mathematics. We will refer to Bishop in a further step. Semantics and syntax need each other. Example. In order to answer the question, what is a mathematical proof, Hilbert used syntactic means visibly in the structure of a formal system. On the other hand, in order to develop deductive inferences, we need some starting primitive terms and axioms whose choice is a semantic job. Meaning needs correctness and rigor, because in their absence, we risk to fall in imprecision and ambiguity. To give only one example, the basic ideas in formal language theory initiated by Chomsky in the late 50s of the 20th century became totally clear only with Saloma 1973 monograph Formal Languages. The role of syntax in understanding the meaning of various notions and statements is crucial, because a formal definition of a notion X is not able to exhaust the meaning of X. The former is finite, while the later is practically infinite. Very important. The syntactic contextual behavior of a given entity may always add something new to its initial genus differential description. Most notions, terms, and symbols in logic and in computer science are in this situation. All these facts show the cooperative synergetic aspect of the syntax semantics correctness meaning interaction. However, meaning may coexist with some benign variants of incorrectness, while syntactic correctness may coexist with absence of meaning, like in Chomsky's famous example, colorless green ideas sleep furiously. Dominating mentality in the 20th century, pragmatic factors make it impossible to check totally the correctness of a mathematical text, because this requires to check what is behind it too, and by regression this is an endless process. The formal system way of life cannot be realized in the everyday mathematical activity for pragmatic reasons, acknowledged by, for instance, by the Bourbaki group, the highest standard of rigor achieved in the 20th century. Computer-assisted activities essentially involved today at the syntactic level of mathematics add new difficulties in checking the correctness of some inferences and statements. The assessment of papers submitted for publication to research journals is faced with increasing difficulties in many cases. The referee's job is concerned with correctness less with meaning. Here is a citation from a paper by Nathanson in the Notices of American Mathematical Society 2008, Desperately Seeking Mathematical Truth. Many, I think most papers in most literary journals are not refereed. There is a presumptive referee who looks at the paper, reads the introduction and the statements of the results, glances at the proof, and if everything seems okay, recommends publication. Some referees do check proof line by line, but many do not. Semantic factors at all levels. Elementary level, the meaning of zero, the meaning of the number pi. See my previous lectures. The meaning of a tangent to a curve, starting from the case of a circle. You know that in high school, students never learned what does it mean, the tangent to a curve. There is an initial definition in the gymnasium of the tangent to a circle, and it is supposed that this definition remains valid for any curve, which is not at all true. Higher level, length of a curve from Jordan to Lebesgue and Fréchet. Also, it is a very problematic thing. most students in university never learn the right definition of the length of a curve. What is a transitive cardinal number? What is a fractal? The meaning of a theorem related to the meaning of its proofs. In most cases, the proof of a theorem tells us more than the statement of the theorem. But we don't pay attention to this. For very long proofs by a large number of authors, there is a danger that each author understands his local part, but no of them is capable to bridge all parts in a whole. See the cases of the theorem of classification of finite simple groups. Two problems appear here: the semantic versus the syntactic understanding, and the whole versus parts understanding. Unfortunately, mathematical activities at all levels, learning, elementary, high school, university, teaching and research, are mainly syntactic. The meaning is marginalized. Pragmatic factors. All issues under the label of didactic and pedagogy belong to pragmatics. Here are also all rhetorical procedures. The way we use our voice, our diction, the way we alternate I teaching or in our lecture, in teaching or in our lectures, computer facilities and traditional means, the way we alternate computer facilities and traditional means, chalk and blackboard. In the field of pragmatics are included all means we use in order to make clear and attractive our message in teaching and in our lectures. Similarly, the quality of our written text, of our articles, of our textbooks, of our monograph, of our email messages, of our everyday interaction with other people, with our students and with our partners, is strongly related to pragmatic factors. Failures in education and in scientific communication are to a large extent due to pragmatic aspects. To give only one example, the way our article or our book is organized, the choice of the right title and the right subtitles determine to a large extent who will pay attention to it. For more than 2,000 years, the logic of science was that of everyday life. Proofs are used in everyday life. There is a whole field of research as interferences, logic, linguistics, law, psychology, sociology, literary theory, concerning the way people argue, argumentation theory. The literature in this respect goes from classical rhetoric to recent developments such as parallel. In the field of natural languages, the distinction between syntactic, semantic, and pragmatic aspects is well established, also it is recognized that no sharp border exists between them. Things are less investigated in the field of heavy sciences, in mathematics and in information science. For more than 2,000 years, beginning with Pythagoras and Euclid, no attention has been paid to the way theorems are proved. The logic of science was the same as the logic of everyday life, based on the classical principle of identity, not contradiction, detectivity. If the need to differentiate the language of science from the language of everyday life appeared already in the 16th and 17th centuries, when the artificial component of the mathematical language became of the same importance as its natural component, the need to check the logical accuracy of proofs appeared only towards the end of the 19th century and the beginning of the 20th century. Also, the appearance of the non-Euclidean geometries already in the first half of the 19th century warned the scientific community about the need to transgress Aristotle's logic. Crisis, hopes, and deception. Russell, Hilbert, and Goethe. The work done by Russell and Whitehead, and especially by David Hilbert in the first and the second decades of the 20th century, aimed just to propose a more rigorous idea of a proof, able to avoid the difficulties which appeared in Cantor's set theory of transitive cardinals and ordinals. These difficulties were related to the fact that some sentences challenged the scientific community by their status in conflict with the principle of non-contradiction. They were both true and false. However, the dream of Russell and of Hilbert to formalize the word mathematics to reduce the problem of correctness of a purely formal mechanism failed, as it was proved by Gödel in any formal system of the type conceived by Russell and Whitehead. For arithmetic, there are some undecipherable statements such as neither they nor their negation can be proved inside the respective formal system. This crisis of the syntactic dimension of any enough complex formal system came as a shock for the whole scientific community. Let us see the details of these events. Hilbert's idea of a proof involved both syntactic and semantic aspects. Hilbert introduces his formal system in the framework of a theory of proof. A formal system given by a finite alphabetical language of array, where A is a union of two disjoint languages M and A of array. Elements of A are called terms, while those of N are called relations. A subset of T of N is considered whose elements are called theorems. Hilbert's idea of a proof involves both syntactic and semantic aspects. As an example, let us take this alphabet formed by 4 elements and n formed by n repetitions of this dot. T is that part of n where n is strictly smaller than n in relation, n is equal to n is a relation, equal, and n is strictly larger than n is a relation. Clearly, the example we just gave is a formal system of the arithmetic of positive integers. In a scientific theory, we distinguish some concepts, some statements, and among statements, some true statements. An interpretation of a formal system into a scientific theory is a mapping from the formal system into the scientific theory F, where to any term in S corresponds a concept in F, to any relation corresponds a statement in F, and to any theorem corresponds a true statement in F. For instance, F is arithmetic of positive integers, and F is an interpretation of the above formal system, where terms correspond to positive integers, relations to all possible inequality or equality relations between positive integers, irrespective of their truth value, while theorems correspond to those inequalities or equalities that are true. Now, the distinction between the syntax and the semantics of a formal system is clearly operated. The representation of the system by its components defines its syntactic component, while the possible interpretation of the formal system into other systems defines its semantic component. Proofs as demonstrative tests, the syntactic-semantic contrast. In the above presentation, theorems are introduced in a descriptive way that does not allow to see how theorems are obtained. In order to generate the theorems, Hilbert considers a subset D of M, whose elements are called axioms, and a finite set of rules transforming in a mechanical algorithmic way some relations in some other relations. A demonstrative text in the formal system is a finite sequence of relations, such that any relation in the sequence is either an axiom or it is obtained from the preceding relations in the sequence by applying some rules. Any relation that appears as a term in a demonstrative text is said to be a theorem. It follows that axioms are a particular case of theorems. Two kinds of models, cognitive and interpretative. When a formal system is interpreted into a scientific theory, we say that the scientific theory is a model of the system, of the formal system, and that the theory, the scientific theory, has been formalized by means of the respective formal system. Such interpretative models should not be confused with the cognitive models. The example we gave of interpretation of a formal system into the arithmetic of positive integers show that the two types of models may be in a reciprocal relation. If F is an interpretative model of S, then S is a cognitive model of F. but we should be cautious with respect to a possible generalization of this statement to any way its converse is not, in any way its converse is not true. With respect to the syntactic-semantic distinction, it is clear that proofs as demonstrative text are purely syntactic devices, but by mediation or possible interpretation of the formal system in which the pieces of a demonstrative text are embedded, the semantic side is shown in its place. However, there is a contrast between the explicit and formal nature of the syntactic dimension of a proof and the indirect and interpretative nature of its semantic dimension. The former is abstract and rigorous, but strictly combinatorial and generative. The latter is looking for concrete instantiations and may take profit from imagination in using analogy and metaphor. Each of them is in its specific infinite. In what sense the semantics of a formal system is richer than its syntax? The infinite possibilities of syntax do not mean its total freedom. Gödel's incompleteness theorem states that every formal system which is finitely specified, rich enough to include the arithmetic and consistent, is incomplete. That is, there exists an arithmetical statement which can be expressed in formal system, is true, but is not provable within the formal system. Condition 1 means the existence of an algorithm giving all axioms and inference rules. Condition 2 means that all the arithmetical symbols and axioms are included in the formal system. Condition 3 means that the formal system is free of contradictions. Any provable statement is true, but the converse is no longer valid. By true arithmetical statement, we mean a statement about non-negative integers that cannot be invalidated by finding any combination of non-negative integers that contradicts it. The discrepancy between true and provable is the kernel of Gödel's incompleteness theorem. It shows that semantics is genuinely richer than the syntax, because only a negligible part of the true statements in a formal system includes provable statements. The word negligible has here a precise mathematical meaning. See, for instance, the work cited there on 94. As we have seen, correctness and rigor on the one hand, meaning and understanding on the other hand. As we have seen, another way to distinguish semantics from syntax is to relate the latter to correctness and the former to meaning and understanding. Are the inference processes correctly accomplished according to the rules adopted in the considered formal system? A positive answer to this question is a sign of the validity of the syntactic component of mathematics and its standards of rigor in the second half of the 20th century. As a matter of fact, it is not necessary to have the explicit presence of a Hilbert-type formal system, as it happens in axiomatic set theory. It is enough to adopt an accurate axiomatic deductive thinking, as it happens, for instance, in the famous treatise of Nicolas Bourbaki, the collective author of a global structural picture of mathematics, counting several tens of volumes published mainly in the second half. Maybe this Bourbaki treatise is the most important synthesis of mathematics after Euclid. Maybe, I don't know. Semantic questions related to meaning and understanding show their increasing importance mainly in the last quarter of the 20th century, after the appearance of mathematical proofs using some computer programs. However, already in the third quarter of the 20th century, with the emergence of the Bourbaki program, where the only explicit semiotic dimension was the syntactic one, mathematicians such as René Thom, Tilswedel, warned the mathematical community about some dangers related to the tension between syntax and semantics in mathematics. This tension is expressed by the conjugate pair, rigor meaning. Any improvement of rigor is obtained at the expense of meaning. And conversely, more meaning implies less rigor. The proof is no longer an exclusive logical activity. The use of computer programs in a proof introduces in what was before an exclusively logical activity an empirical experimental factor and with it a psychological and social component. The first event of this type happened in 1976 with the proof of the four-color theorem. But in this way, some steps in the proof can never be verified by humans. Successive improvement of the proof of the four-color theorem led to its proof by Robertson, Sanders, Seymour, and Thomas, 96, where, however, the basic shortcoming persists. The authors acknowledge that they did not prove the correctness of the compiler by means of which the programs were compiled, and they did not prove the infallibility of the hardware they ran their program on. This had to be taken on files, and so they became a source of error. The authors of the 96 proof of the four-color theorem consider that verifying a computer program is much more difficult than checking a proof of the same length. Understanding is difficult when the length of the proof is increasing. Proofs using computer programs are usually long and have several authors. Each of the authors has a personal understanding of his part in the proof, but it may happen that none of them has an understanding of the proof as a whole. As we have already pointed out, local understanding may coexist with absence of global understanding. But even in the case of purely deductive proofs, it may happen to reach a divorce between local and global understanding. The theorem giving the classification of finite simple groups has about 300 different authors whose contribution is spread in 500 separate articles with a total of 15,000 pages. Biological and sociological factors involved in the status of a theorem. Each author had a personal control of his own contribution, but the general belief was that the only person having a global, holistic idea and understanding of the theorem of classification of finite simple group was Daniel Gorenstein. It happened that Gorenstein died in '92. It takes time to find somebody replacing Gorenstein in this respect. We are here faced with the dramatic fate of some mathematical tools whose status may depend not only on logical factors, but also on biological and sociological factors which are beyond the control of the mathematical community. The theorem of classification of finite simple groups is not an isolated case. Fermat's theorem was proved by Andrew Wills, but checked only by a small number of specialists in the field. The fact that we have here not only one, but several Gorenstein does not change essentially the situation. We believe the experts, also their number may be very small. This belief is, however, at the expense of understanding. The semantic dimension is still in crisis. The dramatic case of Kepler's conjecture, going now back to computationally assisted proofs, we will refer to the dramatic case of Kepler's conjecture about the densest possible packing of unit spheres into a container. The proof proposed by Thomas Hales in '98 is so long and based on so much massive computations that the task of checking its correctness appeared as a very difficult job. Then Thomas Hales started a new project called Formal Proof of Kepler's Conjecture. A comment by Zygmunt, 2004, gives all the details in this respect. It seems that this formal proof of Kepler's conjecture will require 20 man-years to check every single step of Hales' proof. Proof is respect to the inductive, deductive, abductive triad. This aspect was analyzed in some of our previous papers, but we will recall here only the following example where each of the types of inferences, the considered triads, shows its specific. there are 256 tennis players that should compete in a elementary championship. In the first round, there are 128 players. Each of them having exactly one winner and one loser. In the second round, the remaining players will compete in 64 plays, and so on until the last step when two players will fight to the title. What is the total number of players will play? The answer can be obtained in three ways. One mainly inductive, the second mainly deductive, the third mainly abductive. The inductive approach will proceed step by counting and simple addition of the numbers of confrontations taking place at each round. We reach 255. The deductive approach will observe that the terms of the addition above form a geometric progression and will take advantage of the formula giving its sum. The abductive approach, the best, is the shortest one and uses the simple fact that on the one hand, there is a one-to-one correspondence between the set of plays and the set of losers, and on the other hand, excepting the champion, each player is a loser. However, this example should not be understood in a narrow way. As we have pointed out in some previous, each of the three types of inference has its field of excellence. The abductive approach is the most creative because it is the best in exploiting heuristic capacity. The inductive way is the most accessible and the most popular. It makes possible to avoid to transform mathematics in a tautological activity. The deductive reasoning is the nearest to rigor and certainty. Each of them needs the other. None of them can be confused with the other ones, also their border may be fuzzy. Pragmatic enters again the scene. Boris, in a formal system, the pragmatic dimension is given by the relation between S and its user. So the pragmatic dimension of a mathematical proof consists of the interaction among the proof, on the other hand, its authors, and its users on the other hand. This way to understand pragmatics is consistent with the way the classical semiotics understands the triad syntax semantic pragmatics. Following Morris, science has three types of relation: to other science, to objects, and to a person or persons. These disciplines dealing with these three sign relations were called syntactics, semantics, and pragmatics. Later, Morris analyzed the process involving signs, which he called semiosis, a term coined by Peirce. Morris considers semiosis as a triadic relation among a sign vehicle, a designatum, and an interpreter, and he defines syntactic, semantic, and pragmatic as the study of a number of dyadic relational dimensions which he abstracted from it. Morris, 38, identifies the syntactic dimension of semiosis as a relation of sign vehicle to sign vehicle. This is a complex sign of sign system. The semantic dimension as a relation of signs to their designata. The pragmatic dimension as a relation of signs to their interpreters. Morris proposed the term syntactic just to differentiate the syntactic dimension of a general sign system from that of a natural language for which we use the term syntax. Natural programming and mathematical language. It is well known that in natural languages there is no possibility to make a sharp distinction between semantics and syntax. Their border is fuzzy. We cannot avoid the interference of some semantic factors in the syntactic description of a language. Similarly, no sharp, rigorous distinction between pragmatics and semantics is possible. Some pragmatic factors are involved in some semantic descriptions. The situation is different in programming languages, where these distinctions are more rigorous because they are established by convention. What about the mathematical language? In that part of mathematics, which has the status of a formalized field, according to Hilbert, the distinction among syntactic, semantic, and pragmatic is precise, just because it is the result of a convention. However, a large part, the largest of mathematics, is not formalized. And we know from Gödel's incomplete theorem that mathematics cannot be entirely formalized. So the considered distinction cannot avoid situation of interference and imprecision. As a general trend, to the extent to which a programming language or the mathematical language is effectively used, it acquires more and more some features belonging to natural languages. In other words, the increasing of the pragmatic dimension of a programming language or of the mathematical language moves it away from the status of a formal language, bringing it nearer and nearer to natural languages. Some examples will bring light in this respect. Mathematical notions are introduced by definitions, but as soon as they are used, they acquire context-dependent features. For instance, the behavior of zero in its various contexts is much richer than it can be understood from its initial definition. In the same order of ideas, mathematical notation, denotative in its initial form, acquire connotative aspects too, as a symbol of the integral of a real function of a definite real interval shows. Metaphorically, integral of fx dx is not the concatenation, the meaning of this sign is not the concatenation of the meaning of its components. It has nothing to do with this. Metaphorical and metonymic aspects cannot be avoided in mathematical symbolism and terminology. We often use the symbol fx to denote the function f and not its value for the value x of the argument. We use some symbols metaphorically before giving them a meaning, as it happens with the symbol of a series in absence of the existence of its sum. During 2000 years from Archimedes till 18th century, the symbol of infinite sum was a metaphor. Another pragmatic aspect is related to complexity. If a proof aims to reach a certain entity, but the algorithm proposed in this respect is of too high complexity, then the proof is practically useless. Generally speaking, all the problems concerning the cost of an algorithm in terms of its complexity belong to the pragmatic aspect of mathematics. It happens that a lot of important social problems have received solutions that are obtained in exponential time, and this fact makes them of little practical values. One of the most important changes in the methodology of science in the second half of the 20th century was the proliferation of cognitive models in both natural and social science. Many of these models are mathematical, and the theorems, together with their proofs involved in their construction, are appreciated with respect to their position in the modeling process. But cognitive models are appreciated not in terms of true and false, it is their adequacy and relevance in the modeling process which decides their quality. So it is not enough to check the truth of a theorem involved in a cognitive modeling process, it is also necessary to check the relevance of the respective theorem in the modeling process. This means its explanatory capacity in the respective process. This is a typical pragmatic problem. Correctness and meaning get often in conflict. Precision and exactness are often obtained at the expense of truth. Presque écrasement empêche de mentir, is the old French saying. A photograph is more exact than a portrait, but the latter may reveal more artistic truth than the former. Einstein, insofar as the propositions of mathematics are certain, they do not refer to reality. And insofar as they refer to reality, they are not certain. Socrates, rigor needs to replace the real world by a fictional one. René Thom, Tilsweller, rigor is obtained at the expense of meaning. More rigor, less meaning. Again, René Thom, there is a conflict between to see and to understand. The former is a continuous pattern, the latter is a finite small number of parameters. At some moment, as we have seen, rigor was aimed just to make meaningful the idea of a mathematical proof, and it led to Hilbert's formal system. But in some further steps, the development of formal approach led to the marginalization of meaning. Nelson, meaning and rigor in calculus. In the evolution of calculus, the move from Newton and Leibniz to Cauchy and Weierstrass replaced semantics by syntax and dynamics by statics. Leibniz infinitesimals had meaning, but their meaning came only in 1960 with Abraham Robinson's non-standard analysis. And they had dynamics. The epsilon-delta approach of the 19th century brought rigor, but considerably loss of meaning. Dynamics was replaced by statics, claims Nelson. However, Cauchy and Weierstadt with their rigor made more meaningful the basic ideas of calculus, and the same did Robinson with Leibniz infinitely small. And here is paradoxical, conflicting nature of this thing. It is true that in this way it seems lost in dynamics. The temporal aspect has been pushed away, but paying this price, they gain in both rigor and meaning. Triumph of correctness, decline of meaning. Nelson describes the today's situation with a critical. Nelson is professor in Princeton. What is real in mathematics is simply the formulas and proofs themselves as strings of symbols. He claims that this is the dominant mentality in today's mathematics. Only syntax matters. Syntax and correctness decide what is published. Meaning is considered by many mathematicians and computer scientists as something belonging no longer to mathematics but to philosophy. This attitude dictates the style of mathematical education too. There are, however, voices claiming that we do desire more from computation than simple symbol manipulation. Thurston, Fields Medal, accent on history, motivation, questions. He proposes for mathematical education to replace the usual scenario, definition, theorem, proof, examples, applications, by another one with accent on questions, hypotheses, history, motivation, scientific, cultural context, explications, often problems. Bishop, mathematics is common sense. Do not ask whether a statement is true until you know what it means. Very rarely happens this. A proof is any completely convincing argument. Such proposals bring mathematical proofs near to argumentation theory in contrast with Hilbert's attempt to separate them. And René Thom joins this view. Bishop also adds, meaningful distinctions deserve to be preserved. Halmosh, mathematics is never deductive in its creation. The mathematician at work makes vague guesses, visualizes broad generalization, and jumps to unwarranted conclusions. He arranges and rearranges his ideas, and he becomes convinced of their truth long before he can write down a logical proof. The conviction is not likely to come early. It usually comes after many attempts, many failures, many discouragement, many false starts. None of these things is visible in mathematical education. Halmosh again, mathematics is not a deductive science. Mathematics is not a deductive science. It is a cliche to say mathematics is deductive. When you try to prove a theorem, you don't just list the hypothesis and then start to reason. What you do is trial and error, experimentation, guesswork. Halmosh points out that mathematical activity includes all types of inferences: induction, deduction, abduction, both hemispheres of the brain, reflection, experiment, empirical and theoretical approaches. Thom proposed to abandon Hilbert's idea of rigor. He required to adopt another one according to which a proof is rigorous if it is accepted by the professional community of the respective domain, as Bishop said. In this way, rigor is no longer an exclusively logical matter. It is impregnated with psychological and social elements too. Plausibility arguments may become relevant. Recall the famous book Mathematics by George Poya, Mathematics and the Plausible Reasoning. This attitude recalls that of Bishop previously presented. Formal and rigor may be in conflict with history. Formal rigor is often obtained by paying the price of a very artificial way improving axiom. A typical example is a formal proof of the Lagrange mean value theorem in calculus by means of some associated function whose source remains a mystery. In a more general setting, we may say that for reasons of logical formal accuracy and elegance, the historical order of things is replaced by another one that can be just the opposite of the natural order. We learn about sets, function, limit, continuity, derivative, integral, but their historical order has been just the opposite. Great mathematicians about correctness versus meaning. Charles Sanders Peirce, David Hilbert, John von Neumann. What he said, Charles Sanders Peirce pioneered. Some of these claims are still controversial. The following domains where semantic problems prevailed. I want to show you that the great mathematicians paid most attention to semantics, not to syntax. Many-valued logic, statistics, decision theory, predicate calculus, axiomatic foundation of sets. You see, for all these things, we refer to European authors, Peano, Frege, etc. And all of them are in Peirce's manuscripts, which are published now. The idea of recursiveness, let this or exist in Peirce's work. Bridging logic and electrical engineering. The PhD work by Shannon in the 38. A rigorous status of light is infinitely small. Definition of the matter as so many wavelengths of light of a certain frequency. This definition remained in use until 83.
How many volumes did you say? How many volumes of Peirce?
All of these were pioneered by Peirce.
But you said there are like 40 volumes of his works?
Yeah, his work is in, published now. There are programmed about 30 volumes, but they were published so far only about 6 volumes. Affinity between mathematics, Cauchy, and music, Bach. Here is a citation from Peirce, very relevant for the incapacity of mathematics children learn in school to give an idea of the very nature of mathematics and for the affinity between mathematical creativity and musical creativity. What he said Peirce, there is certainly more affinity between reading a memoir of Cauchy and intelligently listening to a fugue of Bach than there is between schoolboy lesson in elementary geometry and a study in the higher mathematics. This is clearly already in the 19th century a clear picture of the way mathematical education fades. Peirce is bridging music and mathematics in the tradition of Pythagoras, Plato, and Kepler. Let us recall that Lalescu, a Romanian mathematician, pointed out in the same order of ideas that Shakespeare is nearer to Poincaré than to Émile Zola. Émile Zola, a second-order writer, but is much farther from Poincaré, from Shakespeare than is Poincaré, who is a mathematician. Today, Bach's fugues are recognized as having a mathematical structure. See in this respect Carl Sandburg's Numberman, a poem. This is an American poet 100 years ago for the bust of Jonas. In view of their semantic weight, most problems in the Hilbert list are either unresolved or not completely solved. Most of them involve the roots and the foundations of mathematics. Its axiomatic base, the basic dichotomy is finite infinite, prime, non-prime integers, algebraic transcendental, rational, irrational, numbers, algorithmic, non-algorithmic. Among the 23 problems in Hilbert's list, only 8 of them are completely solved. Some of them are not yes-no questions. They are semantic. But questions of degree and typology, leaving room for interpretation and opinion. I want to show you that great mathematicians paid main attention to semantics. We give here the situation of the first 10 problems in the Hilbert list. One can see that only 2 of them are completely solved. First problem, the continuum hypothesis, considered resolved by many mathematicians after the result of Gödel and Cohen, establishing its status of independence, but still considered unresolved by authors such as Martin Davis and Raymond Smullyan, asking for a new axiom system for set theory, according to which a yes-no answer could be given to Hilbert's question. Second problem, consistency of the axiom of arithmetic. No consensus despite Gödel's result. Third problem, about polyhedra of equal volume. Clear negative answer. Fifth problem, can the assumption of differentiability for a function defining a continuous transformation group be avoided, solved in various particular cases by John von Neumann, Montgomery Zipfin, Yamabe, and Gleason, but not in general case. Sixth problem, can physics be axiomatized? No complete answer. Seventh problem, let an algebraic different from 0 and from 1 be irrational. Let A algebraic different and B irrational. Is then a power B transcendental, partially solved by Gelfand. The case of B transcendental is not yet solved. Eighth problem, prove the Riemann hypothesis, not yet solved. Ninth problem, construct generalization of the reciprocity theorem in number theory, only partially resolved. Tenth problem, does there exist a universal algorithm for solving the Diophantine equations? Completely solved in the negative, well known. It is also interesting to look at the problems considered by John von Neumann. Most of them are concerned with the foundations of science, where semantic aspects are decisive. Foundations of set theory, foundations of quantum mechanics, foundations of computing, foundations of strategic game, foundations of life. And here is references I used. Thank you for listening. Thank you very much.
Any questions?
Thanks. I'm not a mathematician, but that was still quite interesting. This may not be as important in mathematics, but you didn't say a lot about pragmatics. And in natural language, semantics determines meaning. Okay, yes. We have to understand the speaker's intent in making an utterance in order to understand the meaning. And the same statement with the same semantics can have many different meanings depending on what the speaker is trying to accomplish by saying it. And I think to some extent, this is true in the way we understand mathematical ideas, particularly when they're transported out of the realm of mathematical theory and into the culture. The Gödel incompleteness theorem is a very important example because it has a lot of status in the culture. People refer to it all the time, and they use it to persuade, convince, perhaps to insult people or display their own brilliance or whatever use they're making of this kind of assertion. And so the pragmatic level is very important. Also with statistics, which are often used to convince people to take some course of action, to believe that some treatment is effective or ineffective, that something is or is not dangerous. And so those are meanings that go beyond semantics.
Well, what is the question?
Okay, so I guess my question is, as a mathematician, do you think that this is important in math education and in the way that mathematicians think about the work that they do? What use is going to be made of it?
So the question is about aspects of pragmatics
Yeah.
that add to the definition of semantics in new ways, and whether those should be taught in mathematical education. That add to, meaning has a social way of.
But what there are different meanings of pragmatics. Pragmatics in a formal system, pragmatics. Anyway, in all definitions of pragmatics, their common denominator is the presence, essential presence of the people who is using.
Exactly.
Right.
So, this is obligatory. I could say the main, in computer science for instance, the main pragmatic problem in the last decades is the complexity problems. This is problems where the question is how to find algorithms of lower complexity than the existing ones. I think this is the most frequent problem investigated. If you take all these proceedings of the conferences.
Absolutely. In the algorithm.
This is, I think, but obviously this problem is not only pragmatic. This problem involves all factors, also syntactic, but it is related to the, you see, we had this evolution in 3 steps in the 20th century. First step, about whether the existence of an entity is only potential or effective, which raised Brouwer's intuitionist, etc. Second step, the problem to build a rigorous idea of algorithmic thinking, middle of the past century. And third step, the problem of the cost of work, which is already, it appeared only in the second half of the past century, but it is in the center of attention in von Neumann text in the 40s. But it was an isolated case because in the 40s the mathematical world was not interested.
Ready.
It was too early for this. This is a way to understand pragmatics. But obviously we have a lot of pragmatic problems related to the way we write our papers, the way we teach, the way we give lectures. There are a lot of aspects of pragmatics. The way we alternate PowerPoint with chalk and blackboard and so on. But in most situations, all these aspects are all involved, syntactic, semantic, and pragmatics. The problem is that, and this does not concern only mathematics and computer science, the interest for meaning and understanding is marginalized in all fields. also in the field of humanities, in the field of the main care in teaching is to teach according to this American slogan. It is the slogan, know how. How it will work, procedures. Most thinking, most teaching is interested to show procedures, how to proceed. And this led, I remember already in the 70s, this American metaphor, the ironical description of this type of teaching, cookbook mathematics. In French, mathématiques, recette de cuisine. This is still dominant today now. This is examinations are oriented and assessment. How do you apply some algorithms, some rules, some syntactic? Because it is easier. Syntactic side allows you, how do you call it? Barrel. In order to make a rigorous evaluation of works of students and examinations, obviously you can do it rigorously where you are concerned with syntactic aspects, because you can decide whether he applied or not correctly some rules, some procedures. For the semantic side, no rigorous way to evaluate exists. And so, for a practical reason, for instance, this, is the name of this procedure, that they have only to answer,
Multiple
to choose
questions.
a variant, I'm not going to say that.
Multiple choice.
Multiple choice. Multiple choice. No, here is, he has some advantage. The multiple choice has advantage that you can check the capacity of the students to guess before proving. Because anyway, obviously, generally, before trying to prove something, you try by your intuitive perception and you to get
Yes.
an impression before you prove. And this was Blaise Pascal in the 16th century. He said, we are looking only for things we have already found. What does it mean? That we find something by intuition, by then we try to confirm what we found, to confirm it by rigorous procedures. Otherwise, you cannot know in what direction to direct your effort, your attempts to. How do you choose the theorems you want to, the conjectures you want to transform in theorems? No? But this is not, the guessing capacity is not developed in education. In education, it is only the show that. This is William Thurston. Observe this is why he proposed to change completely the today way to teach mathematics to common people. To teach mathematics to common people, to people who will not be mathematicians. It's a completely different job than to teach mathematics to the possible future mathematicians. Completely different. And Thurston captured this, but his voice remained an isolated one. And,
Who was that? Who-
William Thurston,
Oh, Thurston.
geometer.
Okay.
Any other questions? Thank you very much again.